Hi all, this is lecture 22 on section 11.3 on the integral test. So we're going to continue on our journey on trying to identify how we can determine convergence for series. Okay, so far we know what to do with a harmonic series, with a geometric series, and with a telescopic series. What we don't know what to do is with everything else. So let's think about this series for a second. If I have the sum n equals 1 to infinity, we know that 1 over n is harmonic, but 1 over powers of n are not harmonic. So what does this do? So let's take a look at our first couple of terms here. So if I plug in 1, that's 1. If I plug in 2, that's 1/2. If I plug in 3, 1/4. If I plug in 3, that's 1/9, right? So on and so forth. Okay. Now, I want you to think about the graph. If we think about this as 1 over x squared, the graph of 1 over x squared looks like this, right? And let's think about it from 1, and x equals 1, to infinity, because that's what we're working with, right? So here's 1. And so this point is at 1. Okay, so I want you to think about for a second estimating the area under this curve, right? Let's take our interval to be 1 so that we're working with the values, the whole number values. And essentially, we're going to create these rectangles. Now, because the width of our rectangle is 1, right? This distance is 1. So the area of the rectangle that we create is going to be just whatever the height is, okay? So if we estimate using left endpoints, that gives me this rectangle, and this rectangle, and this rectangle, and this rectangle, and we can keep going all the way out to infinity, right? So what is the area of each rectangle? Well, the area of each rectangle is f of 1, right, because it's the left side, times the width, which is 1, plus f of 2, plus f of 3, plus f of 4, so on and so forth. Well, that is just, this is left endpoints, by the way. If I plug in 1 to my function into 1 over x squared, that's 1. Plugging 2 into the function is 1/4. Plugging 3 is 1/9, so on and so forth. So essentially, looking at the estimate for the area under the curve using left endpoints is exactly the same as the values in my series, right? So the things that I'm adding up here looks exactly like the estimation for the area under the curve, okay? So that tells us that because these two things are equal, then if the area under the curve converges, then our series converges. But what is the area under the curve? The area under the curve is the integral from 1 to infinity, because that's where we're headed, of the function 1 over x squared dx. So then if that converges, then the series n equals 1 to infinity of 1 over n squared converges. Okay, and that's the basis for our integral test. So essentially, if we look at the integral of the corresponding function to our series, and that converges, then our series converges, okay? And that's what our integral test says. So the integral test says, suppose f is a continuous positive decreasing function, right? It's continuous, it's positive, it has to be decreasing. If it's not decreasing, then there's no way that it's going to converge, okay? On the interval from 1 to infinity. And then we let an equal f of n. So this an here is our series values, or our sequence values that we're going to add up. And then f of n is a function. Then the series is convergent if and only if the improper integral is convergent, okay? And so that tells us that if my integral is convergent, then my series is convergent. If my interval is divergent, then the series is divergent. So here's what the example will look like. So the first thing that we can do is, this is what we can use to show that the harmonic series diverges. So if we know that this harmonic series, sum n equals 1 to infinity of 1 over n, The corresponding integral, to apply the integral test, we're going to look at the function of 1 over x, and we're going to integrate it from 1 to infinity dx. Okay, this is improper integral, so we're going to replace the infinity with a t and take the limit as t goes to infinity. And so it's the limit as t goes to infinity, integral from 1 to t of 1 over x dx. But this is just the limit as t goes to infinity of the natural log of x, absolute value, although I don't need it because these are all positive, from 1 to t. And that's the limit as t goes to infinity of natural log of t minus the natural log of 1. We know that the natural log of 1 goes to 0. And so this is just the natural log, the limit as t goes to infinity of natural log of t. So this is the natural log of infinity, which turns out to be infinity. And when our limit goes to infinity, we say both diverge. So the harmonic series diverges due to the integral test. Okay. So anything that we can integrate, we can use the integral test for. So as long as the function is positive, increasing, and positive, decreasing, and continuous, we can use this. Okay, so for the next one, take a look. This is something that we can integrate. It's positive. It's decreasing, right? We can look at the limit of ln n over n, and that's going to turn out to be 0. So it is potentially convergent. And if we use the integral test, then we can take the integral from 1 to infinity of ln of n over n. Whoops, I don't want n's, I want x's. Ln of x over x dx. And so we replace our infinity with a t and let our t go to infinity of the same function, dx. All right, now I think what I want to do here to integrate this is to separate them and give them some space so I can see what I'm doing. So that's 1 over x times the natural log of x dx. And I think what I'm going to do here is make a u substitution. So I'm going to let u equal the natural log of x. Then du is 1 over x dx. And so 1 over x dx is my du. So this becomes the limit as t goes to infinity of, now, if I'm going to make this substitution, I want to switch my boundaries. So if I plug in 1 for x, then the natural log of 1 is 0. So my u will start at 0. And the upper bound, if I plug in t for x, that's a natural log of t. And just in case you're wondering, I'm plugging it in here. Okay, so we make that boundary switch. The 1 over x dx is my du. And natural log of x is my u. So this is going to be the limit as t goes to infinity of 1/2 u squared from 0 to the natural log of t. And sorry, I didn't give it a lot of space for this. Let's see what happens next. So we have the limit as t goes to infinity, and I want to plug in my boundaries. So 1/2 ln of t squared minus 0. And then when you take the limit here, this becomes 1/2 infinity squared, which is infinite, and this diverges. Okay, so that's how we use the integral test to determine whether a series is convergent or divergent. Okay. One of the most common series that we can identify with the integral test is about the p series. So p series is another common series that we see. And the p series is the series n equals 1 to infinity of 1 over np. Now, we saw this with sequences, and I showed you this, or actually, I think I did this with derivatives, maybe. I think improper integrals. We did this with improper integrals, where we said, okay, for which p-values does the function, does the integral diverge or converge? Okay, and here I'm telling you that it is convergent if our p is greater than 1. And it is divergent if p is less than or equal to 1. Okay. So that's because we're going to look at the integral. So the proof here is the integral from 1 to infinity, 1 over x to the p dx. And so this is the limit as t goes to infinity, integral from 1 to t of 1 over x to the p dx. Okay, now we want to show that if p is greater than 1, this converges. So if we let p greater than 1, okay, then this is at least, well, it's bigger than 1. So when you take the antiderivative, it's not a special case. It stays in the bottom as something negative. So this is x negative p over x to the p plus 1, right? And that's because this is essentially the same as the limit as t goes to infinity of integral from 1 to t of x to the minus p. So this is wrong. Hold on, let me fix it. So what we get, this is why we take our time, dx. So when you take the antiderivative here, this is x to the negative p plus 1 all over negative p plus 1 from 1 to t. And this becomes the limit as t goes to infinity. I'm going to leave the 1 over negative p plus 1 out front, and that becomes 1 over x to the p minus 1. And as long as our p is greater than 1, then this is going to converge, because when we plug in our t, 1 to t, then this is the limit as t goes to infinity of 1 over negative p plus 1. And we've got, let's see, plug in t, so 1 over t to the p minus 1 minus 1. Okay. So essentially, as long as this piece converges, then the whole thing converges. Okay, so what happens there is we get 1 over negative p plus 1 times, now, if p minus 1, what happens to that exponent if p is greater than 1? So if p is greater than 1, then p minus 1 is greater than 0. So you have a power on the bottom that is greater than 0. And that's going to go to 1 over infinity minus 1. And that's just going to turn out to be negative 1 over negative p plus 1. And so this is convergent. Okay. So that's when p is greater than 1. Now, I did not leave us room to keep going here, so let me try to do that. Create some space. There we go. All right, so this is what we originally had. So now, if we consider other p-values. So what happens if p is equal to 1? If p is equal to 1, then this is the integral from 1 to infinity of 1 over x dx. And what we get here is the limit as t goes to infinity of the natural log of x from 1 to t. And this is the limit as t goes to infinity of ln of t minus ln of 1, right? This is essentially harmonic. And so you know what's going to happen here. This goes to 0. And you get the natural log of infinity, which is equal to infinity, which means it's divergent. Okay. What happens if p is less than 1? Well, when you take this limit, so this is the limit as t goes to infinity, and the antiderivative at that point, right, because now you're working with, hold on, let me write it. You're working with the integral from 1 to infinity of 1 over x to the p dx, where p is less than 1. So if p is less than 1, then when you set this up, we take the limit as t goes to infinity, integral from 1 to t, 1 over x to p dx. And now when we take the antiderivative, this is, again, x to the negative p. So we get x to the negative p plus 1 over negative p plus 1 from 1 to t. And so you have the limit as t goes to infinity of t to the negative p plus 1 over negative p plus 1. And now when you take infinity to a negative p plus 1, what happens with this power? So negative p plus 1, when p is less than 1, means that you're going to get something that is, let's see, if p is less than 1, then negative p is greater than 1. and you're adding 1 to both sides, so negative p plus 1 is greater than 2. Okay, so if you have something greater than 1, now you've got an exponent here that's bigger than 2. So when you take t squared or larger and let t go to infinity, this becomes infinity and it's divergent. Okay, and so that's why the only time that this converges is when your p is greater than 1. Okay, so we want negative exponents are good, positive exponents are bad when it comes to convergence. Okay.